Yeah, welcome to today's seminar talk. So this is going to be the last one for this semester. And yeah, we are happy to have Laura Ryder from UGA to talk about modular perverse sheaves on the affine flag variety.
Yay. All right. Yeah, thanks for being willing to listen to one more talk at the end of a long/short semester. It's been a strange fall. So hopefully mathematics, which is usually the difficult part of our job, becomes the nice, relaxing part for us to think about for a while. Okay, so first, some background or motivation. So I consider a pair of connected reductive algebraic groups. And I want these to be Langlands dual to each other. So if I'm dealing with a connected reductive algebraic group, then they're classified by their root data. And so you want to swap out roots and co-roots and weights and co-weights, and that defines for you a different group that ends up being surprisingly related. And the guiding insight for what I'm going to share with you is that the affine Hecke algebra. So I live next to the train tracks, and so it sounds like the train is coming. So hopefully that doesn't interrupt too badly. So the affine Hecke algebra admits two categorical manifestations. And one is defined in terms of G's information, and the other is defined in terms of the information related to the dual group G check. All right. So for me, I'm not going to say too much about the affine Hecke algebra. We've heard quite a bit about it. I want this to be associated to the affine Weil group. Typically, this is called the extended affine Weil group because it's not always a Coxeter group in the in the precise meaning of Coxeter group. But so you take the Weil group associated to G or G check, and then I let it act on the co-weight lattice. So I want this to be co-weight lattice associated to G. And so this defines for me a group that's almost a Coxeter group. Sometimes it is actually a Coxeter group. Okay, good. So first I'll tell you about this, this manifestation on the G side. So on the G side, this comes in terms of constructible sheaves. So constructible is a fancy word that essentially means that these sheaves are built out of locally constant sheaves. And so the reason that we look to constructible sheaves is because they're a good replacement when you're dealing with categories. They're a good replacement for functions. So this is known as the Grothendieck's function sheaf correspondence. So maybe one of the first ways of viewing Hecke algebras in general was a Hecke algebra associated to a pair. So this was normally a group inside of another group. So let's say that these are just finite groups for our purposes. This Hecke algebra looked like a function space. So this was like functions that were H bi-invariant from G into whatever ring you like. Maybe you want to choose the integers, or maybe you want to upgrade to a field or something. So these were these double coset rings. And then if I wanted to turn this space into a ring, then I needed to use a convolution operation. Okay, so that's what we're doing here, except instead of dealing with functions, we wanna categorify the affine Hecke algebra. So we look to sheaves because there we have more that we can do. So the space that I'm going to look at is I take my group and I extend scalars to the field of Laurent series. And then the subgroup that I'm taking, of course, this isn't a finite group, but when I deal with sheaves, this problem, the problem that arises will not arise. So the subgroup that I want to take is called an Iwahori. So this is the pre-image of a Borel subgroup. So it acts like a Borel inside of this subgroup, and pre-image under the evaluation at 0 map. So this maps me to G. All right. So this is called the affine flag variety. Okay. All right. So the word variety here is a bit of a misnomer. It's actually an end variety, which means it's an increasing union of regular finite dimensional varieties, and actually you can regard it as an increasing union of projective varieties. So it's an end projective variety. You're supposed to think of it as sort of like a finite dimensional flag variety. And in fact, that's true in certain cases. Maybe if I take my group to be simply connected, then this is literally a flag manifold, but for a Kac-Moody group rather than for a reductive group. But in general, if this group is not simply connected, this can have many connected components. So in that way, it's different from a finite dimensional flag variety. Okay, but each of these components looks the same as the identity component, and the number of components is the same as the size of the fundamental group. And finally, since if I'm thinking of the Hecke algebra, I want I-invariant functions on the affine flag manifold. So I need to understand what the constant functions on that space would look like. So there I'm turning to my Bruja decomposition, which tells us that these can be indexed by exactly the affine Weil group that we wrote down before. And again, you have a description where a single orbit looks like some affine space, and the dimension is given by a length function associated to this affine Weil group, and its closure is a projective variety.
Laura, can you maybe move the paper up a bit?
Thanks. Okay, cool. So now instead of studying functions on this space, we're going to study sheaves on this space. And so this is the category we're looking at. So this is the bounded derived category of K sheaves. So this K here means that's my coefficient field, K sheaves, on the affine flag manifold. And then the words that I want to add to this are constructible. So these are built out of locally constant sheaves, and I equivariant. So this little I here means I equivariant with respect to the Ewell reaction. So this category is monoidal. And the monoidal structure is essentially the same as that for functions. It's coming from convolution. So yeah, so I'm not sure if seeing the definition of convolution, I'll write down the definition of convolution. Why not? If I run out of time later, I'll cut the more difficult things to talk about. Okay, so if I want to convolve two sheaves, I need to use some sheaf functor business and some maths. So you start with two sheaves. So you're starting with something on the product of affine flag varieties. And where do you want to end up? You want to end up on a single copy of the affine flag variety. Okay, so the problem is here we want to use our multiplication map, but here we can't use multiplication. So we have to somehow move from this space to a different kind of product where we can multiply. So the way we do that is first we forget the quotient by an Ewell here. And so we just have this and the quotient map. And then now I go to sort of a twisted type of product where I'm allowing my Ewell to kind of move across the product. So this is not a fibered product. This is this, as a set, it looks like ordered pairs, one element here, one element here, and then you have a relation according to the Ewell reaction on the left for the second component and on the right for this first component. But here we can multiply. Okay, so to convolve, what you do is you want to move across this diagram, but the way you move across this diagram is very important. So first you start with your boring product. This is called the external tensor product. And then I pull it back along T. So this P upper star moves me from here to this intermediate space. Okay, this intermediate space is interpolating between these two types of products, our regular and our twisted. And what happens is because I'm equivariant, this P pullback of something has to match with a unique something that's pulled back from over here. Okay, so this something is uniquely defined. Okay, and then you would define the convolution to be, you know, find that something and then push it forward along your multiplication map. So now I move down. Okay, and if you're used to other situations where you have this sort of double coset space, either like on an ordinary flag variety or partial flag variety, convolution is defined in exactly the same way. All right. So this is the category that I want to call the affine Hecke category. And historically, this is the first place that people were looking for the affine Hecke algebra because of the function sheaf correspondence. They understood Hecke algebra to mean functions on double coset, so let's replace that with constructible sheaves. All right, here's a standard warning for the experts. This category that I wrote down as it's defined does not categorify the affine Hecke algebra. It categorifies the group algebra of the affine file group. So there's no, if you think of the affine Hecke algebra as being an algebra over Z adjoined Q inverse, then this category doesn't have the good Q inverse action. So to get that, you need to incorporate the word mixed somehow, and there are different ways to do this. But I don't want to spend time talking about that. All right, cool. Good. So one thing we like about the affine Hecke algebra is it has this super awesome basis, which encodes lots of useful information about representation theory called the Kajdan Lustig basis. So categorically, what this corresponds to is a collection of sheaves called intersection cohomology sheaves, which I'll abbreviate as IC for intersection cohomology. And I have one for each Iwahori orbit, so one for each element of the affine vowel group. And these are examples of objects in a subcategory called the perverse sheaves. So I don't want to say too much about that in here. It's just what's important for you to know is that this is a big category, and it's an example of a triangulated category, which means it has distinguished triangles. And then this perverse subcategory is much smaller. This is an example of an abelian category, and so it looks like modules over a ring, but it looks like modules over an Artinian ring because all objects here have finite length. Okay, and then these IC sheaves in the context of this abelian category, these are the exactly the simple objects. So that's the most you need to understand in order to get through the second half of my talk. Maybe this is a good point to stop for questions. Any questions so far or comments?
Yeah, I have a question, Laura.
Yeah.
So this convolution product, it need not be commutative, is that right?
That's right. Exactly.
And so you have an example of a monoidal tensor category, which is triangulated. Do you know anything about the ideal structure in this category?
Yeah. Yeah. So that has its own complete story. So the two-sided ideals corresponding to this convolution structure are related to Lustig's two-sided cells.
Okay.
And left ideals are related to the left cells, right ideals are related to right cells. So that definitely shows up.
Because we have a sort of theory now for tensor triangulated categories, which are non-symmetric, so non-commutative tensor triangulated categories. So there's a certain, commutative spectrum that I can go along with this category, and be interesting to see what it was, for example. Maybe it's related to the cell theory. So
yeah, that would be interesting.
So you could talk about prime ideals, and then you can sort of topologize them and everything.
Right. Yeah, I'm not sure if I know that definitely people have been studying the two-sided cells and whatnot in this context, but I'm not sure if anybody's thought about trying to associate a associative variety with that using like a max spec type construction or anything. So yeah, that would be super interesting. Yeah, thanks for that.
Okay, thanks.
maybe while I'm at it, as Dan mentioned, so this is the category that you need to take, this bigger category is the category you need to take to get the convolution. If I restrict my convolution operation to this subcategory, perverse sheaves are not preserved. So this is why in this setting, it's really important to be comfortable working with the full derived category and not just the abelian category of perverse sheaves, even though if what you really want is to understand representation theory, you're really looking at the perverse sheaves, but you need this to see the Hecke algebra structure. Good. All right, so now I'm going to tell you how this algebra appears on the dual side. So this is a bit, I mean, to me, this is a bit less obvious, or much less obvious, maybe I'll say. I don't find this to be intuitive at all. So I think my job for this coming year is to understand this more explicitly. So on the G-check side, instead of using constructible sheaves, we study coherent sheaves. So the space that you study is called the Steinberg variety. And I'll tell you what this looks like as a set. So this is usually written as a set of triples. So I have an element that is nilpotent, and I have two Borels. And then I have this incidence condition. So I want the nilpotent to be in both of these Borels, or in the Lie algebra, since I chose it to be nilpotent. So this is what this variety looks like as a set. And it's pretty clear when you write it down in terms of these triples that this variety comes with maps. So I could project onto my first coordinate and end up in the set of nilpotents in your Lie algebra. This is called the nilpotent cone. I could project onto my second and third factor to end up in a product of flag varieties. So this should have a check on it. I could project onto the first and second, or the first and the third. So I have two maps taking me to the Springer resolution. So this is the resolution of singularities for the nilpotent cone, and this identifies with the cotangent bundle of the flag variety. Yeah, so with these two maps, you can identify the Steinberg variety as a fibered product of the Springer resolution with itself over the nilpotent cone. All right, so in this situation, we want to study the bounded derived category of coherent sheaves on the Steinberg variety. And we also want these to be equivariant with respect to the corresponding group. And then we want to tack on an action of the multiplicative group. And these are, I should put equivariant somewhere. G check cross GM. Equivariant. All right, so again, this category comes with a monoidal structure. That's also called convolution. And the convolution structure here comes from the fact that this is a product of two copies of the Springer resolution. So I have to define the convolution, I need to take three copies. And then if I have three copies, then I have three different ways to map down to the Steinberg, right? I can take, I can project onto the first two, or the last two, or the first and the third. down. Sorry, my child is interacting with me. Okay. Okay, so I take my sheaves, let's say F and G on the Steinberg, and I pull it back along these outer maps. So pull back F along the first and pull back G along the last. And then I can tensor them up there. This is really a derived tensor product. And then I push it forward on this middle map. And this is called F star G. All right, so if I'm in this situation, so I'm claiming that this also gives you a category, this category together with the convolution operation that categorifies the affine Hecke algebra. But for me, this is much harder to see. It's completely not obvious to me what the Kajdan, how do you identify the Kajdan Lustig basis, for instance. On the other hand, if you're familiar with the Bernstein presentation, that's easier to see. So let me kind of hint at how that appears using just the geometry of the Steinberg variety. So the Bernstein presentation of the affine Hecke algebra gives you basis elements corresponding to the finite Weyl group, and then you also get basis elements corresponding to the co-weight lattice. But the elements that you choose corresponding to the co-weight lattice form a commutative subalgebra of the affine Hecke algebra. So it's not there. You don't choose the standard basis for that part. So for the finite Weyl group part, what you're looking at is the fact that the irreducible components are exactly indexed by the finite Weyl group. So let me show you how this works really quick, because it's not so hard to see once you're comfortable with this setup. So as I mentioned before, the Steinberg variety maps to 2 copies of the flag variety. And there's standard fact that if I take the G orbits with the diagonal action here, then this is the same as the B orbits on a single flag variety, and those of course are indexed by the Weyl group. And so what do? I take a single G orbit. So X is not a Schubert variety. I mean this to be a G orbit. So not the closure. And then I take the pre-image of it. And this, obviously, this is going to be irreducible because it's a pre-image of a homogeneous space, but it's not closed, so I have to take the closure to get the irreducible component. So these are the irreducible components inside of the Steinberg variety. All right, so each of those closed subvarieties gives you a collection of coherent sheaves, and then you need the commuting things that correspond to the co-weight lattice, or this is the weight lattice for G check. So these correspond to a particular way of pulling back line bundles on the flag variety. All right. And then, yeah, maybe I should mention that this, the fact that this categorifies the affine Hecke algebra, this is due to Kajdan and Lustig. And there's also some exposition written by Ginsberg in the book Kristen Ginsberg. Yeah, so now the theorem. At least when I'm working with all of this stuff in characteristic 0, algebraically closed, the 2 categorifications of the affine Hecke algebra are equivalent as monoidal categories. And so I'm purposefully being a little bit vague here because, like I mentioned for the first, in our first example, when we're dealing with constructible sheaves, to really get the affine Hecke algebra, you have to use the word mixed. And so that mixed structure would correspond to the GM action here. And if you look at Bezrukavnikov's paper closely, I don't think he ever writes that statement down. I think what he writes is the unmixed equivalence, and the unmixed equivalence is complicated in a different way. The unmixed equivalence requires you to, instead of working with the usual Steinberg variety, you have to work with a derived scheme, and instead of working with derived category of coherent sheaves, you have to work with some DG coherent sheaves, and so that statement is also complicated to write down carefully. But it exists, even if it's not well understood by me. Okay, so the hope is to prove Bezrukavnikov's theorem for positive characteristic. As long as this characteristic is not too small. So some of the statements that I've already written down require the characteristic to not be too small. Like if I'm identifying the Steinberg variety of triples with the cotangent bundle, that requires the prime not to be too small. So you have to, we expect there to be some modifications that need to be made to include small primes in this statement. So I'm not going to talk about this today. This is not yet carefully written down. So instead, I'll tell you about some progress in this direction. Okay, so the progress is relating to sort of simpler categories on each side. So let's go back to the G side. Okay, so on the G side, I want to forget my big triangulated category and deal with the smaller category of perverse sheaves. And I don't want to take this whole category. Instead, I want to take a quotient. So I'm modding out by a subcategory. So remember, this is an abelian category, and its simple objects are the IC sheaves labeled by the affine vial group. So I want a quotient by the subcategory whose simple objects are labeled by elements with positive length. Okay, so that means I'm killing almost everything. Yeah, so if I'm in the simply connected case, there's only one simple object left in this quotient. So I'll call this P0. Now this category by construction, it's abelian, it's just a Serre quotient. And as I mentioned, the number of irreducibles becomes drastically smaller. So now this is the size of the number of connected components of the affine flag variety, or the size of the fundamental group. In terms of the geometry, what this means is I have just a skyscraper at each of those connected components. So those are my irreducible objects that don't get killed. All right, now this category does have a monoidal structure, unlike perverse sheaves, and it's commutative. So this is a big deal if you're looking at monoidal structures. This is telling you something. This is telling you that your abelian category looks like a category of representations. So the monoidal structure comes from the convolution on the flag variety. So let's denote quotient of objects with a bar on top. So what I do is I take representatives for those objects in the perverse sheaves, then I convolve them in my affine Hecke category. As I mentioned, this convolution may not be a perverse sheaf anymore, so then I have to do a type of truncation corresponding to the perverse T structure. All right, so yeah, so this category looks like representations of an algebraic group with its tensor product. Okay, the problem is the way this is usually proved for a symmetric monoidal structure is that your category comes with something called a fiber functor. So the fiber functor is a faithful way to get to vector spaces, and it's not obvious what that functor should be. Okay, so I'll tell you how we manage that problem a bit later. But before I get there, I want to tell you the category that appears on the dual side. Yeah, I think I'll just come out and say it. So the category that appears on the dual side is exactly the category of representations of a group. This group is the centralizer in G check of a regular nilpotent element. Okay, so this group this group is well, let me tell you what it looks like for SLN. This is a subgroup of the Borel, and it always contains the center. So for SLN, I get the nth roots of unity. And then it's contained within the Borel, so I can write this down in terms of, say, upper triangular matrices. And then along each diagonal above the main diagonal, I have to get the same number all the way down. And so on. So that's what this group looks like. And in general, you will always have the center. The center is your maximal torus of this non-reductive group. And then you have some unipotent stuff. That'll always be the case. All right, so how does this relate to our original category of coherent sheaves? I want to make a replacement. So instead of working with sheaves on the Steinberg variety, I want to simplify and work with sheaves on just the Springer resolution. And so this category, the affine Hecke category acts on this category by convolution. So if I'm thinking analogously, then I need to take some kind of quotient of this category, and quotient in the context of this algebraic geometry structure means restrict to an open subset. So quotient means restrict to open. All right, so we study the Springer resolution a little bit. It's a resolution of singularities of the nilpotent cone. That means that it's an isomorphism over an open, dense, smooth subset. And it turns out that we can take that smooth subset to be the regular orbit. So this resolution is 1-to-1 over this regular orbit. And so I can view that as just a subvariety of the Springer resolution. And so what I'm doing is, by quotient, I mean restrict to this. So the category that I'm looking at is G-check equivariant sheaves on this orbit, which is the same thing as just doing representations on the stabilizer of a point. And in this case, the stabilizer of a point is the centralizer. So that's why this category appears on the dual side. All right. And then the main theorem with Bezrukavnikov and Riche is that in fact these categories are equivalent. Oops, this should be the centralizer. As monoidal categories, as long as the characteristic's not too small. All right, so in the remaining time, I think I'll talk about some of the ingredients that show up here. Some of it I think is interesting representation theoretically. But before I do that, maybe I'll pause for a second. Are there any questions at this point?
Can you say something about what big enough means? Is it good or bigger than good, like 2H or something like that?
Yeah, it's not necessarily 2H, but good is not good enough. So it depends. The prime needs to be at least good, but then there's an additional condition depending on like which type you're in. Yeah, I wrote this down carefully somewhere. Like you don't want the yeah, if I take the weight lattice modulo the root lattice, then I want that to be free. And then the additional condition I need is that I want the co-weight lattice modulo the co-root lattice to not have any L torsion if L is the characteristic. And yeah, and then there's a stronger bound for type BN, E7, and E8. So for type BN, I need it to be bigger than N. For E7, I need it to be bigger than 19, and E8, I need it to be bigger than 31.
It's like the calculus number.
It doesn't sound very intuitive.
Yeah, probably P bigger than the Coxeter number will be good enough.
Yeah, the problem is the way that we prove this. It requires understanding how tilting modules in, say, representations of the dual group G-check, how tilting modules can be generated by some easy tilting modules under tensor product. So yeah, so there's an argument for this due to Juto, Maltner, and Williamson, where they start with the tiltings which are already irreducible. Those are the minuscule weights, and then you can also incorporate the quasi-minuscule element. So the quasi-minuscule weight has the Weyl group orbit of the weight, and then it also has the zero weight. And so that representation is also allowed. And then you want to see that under tensor product, you can get every tilting module as a tensor, as a summand of a tensor product of those. And so that's the reason for these restraints.
Sorry, I had another question. So how does this relate to like, so there's this classic result by Arkhipov, Bezrukavnikov, and Ginsburg, which sort of relates the dB coherent of G check star cross CM of N tilde.
Yeah.
Perverse sheaves.
Yeah.
And then you also have the small quantum group coming in.
Yeah.
So is this,
go ahead.
Is there a picture like that in this situation?
So their picture is different. because I would say it's causal dual to this one.
Okay.
So at the end of the day, their equivalence does not relate to abelian categories when you're looking at coherent sheaves on the Springer resolution and then the constructible sheaves.
Uh-huh.
It does not give you an equivalence of two abelian categories. So it's like a causal type equivalence.
Well, maybe I should rephrase my question a little bit. So is there some like some algebraic object whose module category reflects dB coherent of the Steinberg variety? So for example, the quantum group sort of reflects things on the level of coherent sheaves for the Springer resolution.
That's a good question. I'm not sure. Somehow you have to keep in mind that that when we take coherent sheaves on the Steinberg variety, we're getting the full affine Hecke category. And so if we want to get module categories for that, then we're looking at where it acts. So that's why this shows up here. This is my algebra, and this is a module for it. So this is going to be more likely to be related to a category of representations, such as the small quantum group, than this one.
Yeah, so they, like, if you look at Ginsburg-Kumar, I mean, it's related to looking at the cohomology.
Yeah.
Right? The cohomologies sort of match up, and that's what gives you the correspondence. So you have to lift the correspondence, of course, but
Yeah.
Okay. Thanks.
Yeah, of course. Okay, so yeah, and the remaining, it's all right. Okay, maybe I'll do this really fast. Okay, the ingredients for this equivalence. So the first ingredient, I mentioned to you, we don't have a fiber functor for this category, so we need a replacement for the fiber functor. And this is not an original idea. This was well understood by Bezrukavnikov along with work of Gatescory before we were even beginning to think about the modular case. So how does this go? I have perverse sheaves on the flag variety, and then I have my quotient to P0. And so the way that I get a group showing up is the following. So I have to look at perverse sheaves on a different space called the affine Grassmannian. The affine Grassmannian is actually what showed up in the picture that Dan was talking about. And so Gatescory shows that there's a functor here. So this is, Z is Gatescory's central functor. So central functor means that there is also a monoidal structure here on the affine Grassmannian. And these, when I apply this functor, these match up with objects in the center of this category. So they commute with everything in the affine Hecke category. And this category on the affine Grassmannian, this matches with representations of the dual group. So this is known as the geometric Satake equivalence. Satake. So now we have a functor going from representations to our P0, and this functor is monoidal. It respects the monoidal structure on rep G check and the monoidal structure on P0. And looks like, and we need to show that it looks like a restriction functor. Looks like restriction to a subgroup. Okay, this is essentially a faithfulness property, because if you think about a restriction to a subgroup, no representation gets killed. So this tells us at the very least that this category is equivalent to representations of a group, and that group is a subgroup of the dual group. Okay, the next step is to see how do I get centralizer of a nilpotent element here. So this comes from the fact that this functor z, this is originally due to Gates-Gorey and then done in a slightly different way by Chinwen Zhu, and we actually need to use his construction of the functor in order to make this work. This functor is given by nearby cycles. So you're looking at a version of the affine flag manifold and the affine Grassmannian over a curve. And when you look at it over a curve, then you specialize to a special point. That's what nearby cycles means. And so when I specialize to a special point, now I have this action of the monodromy going around that special point. So because it's defined by nearby cycles, this functor comes with an automorphism, which turns out to be unipotent. So that tells us that we can regard H as being a subgroup in the centralizer of a unipotent element. So now I've switched from unipotents to nilpotents, but hopefully nobody will complain in the interest of time. So yeah, steps 1 and 2 really aren't new. 3 is where the real work comes in, showing U as regular. This is pretty technical. So this, I mentioned the Bernstein presentation. This is a presentation with that, with those basis elements that commute. So those basis elements correspond to what are called Wakimoto sheaves. And so, so we need to study these carefully in order to see that this element U is regular. And I think that's all I'll say about that in the interest of time. But if there are questions, I'm happy to answer them. And then the final step is to see that H is in fact not just a subgroup, but the full centralizer of this regular unipotent element. And this uses a cool lemma. So I want to write down this lemma. And then I'll stop. So the lemma says if you have a subgroup of the centralizer of a regular unipotent element and it contains the center, then there's a way to test whether this group is the full centralizer or not. And you only need to look at tilting objects. So I'm looking at G-check tilting representations. Okay. Then what I can do is I can take the invariance from the centralizer and I can take invariance from my subgroup. And naturally, there's going to be an inclusion here. And the condition is that, in fact, this inclusion needs to be equality for every tilting representation. And if that holds, then it has to be the case that this subgroup is the full centralizer. So, so we're able to use this lemma and then check on the constructible sheaf side that in fact we have a property like this. So we need to check this in what is called the anti-spherical category. Good. Yeah, and so yeah, so those are the main ingredients to prove this, and then the hope is that somehow if I'm looking at sheaves on the affine flag manifold or coherent sheaves on the Steinberg variety, that since these have the same quotient, this is meant to be similar to Sergel's functor V for category O. So Sergel's functor V takes you from category O, the principal block, to modules for the covariant algebra, and he shows that this functor has lots of really nice properties so that he's able to lift this structure to study the principal block of category O. And so we're trying to do something similar here. And I'll stop there.
Okay, thank you very much. Yeah, any questions?
You mentioned the Kajdan Lustig basis and the coherent side. Is this at all connected with these IC coherent sheaves?
It's possible. The only caveat is that the IC coherent sheaves, like it doesn't make sense to define them on the Steinberg variety. So the place where their definition makes sense is on the nilpotent cone. And so somehow you would have to get from the Steinberg variety to maybe the Springer resolution, and then maybe to the nilpotent cone from there. And it's very possible that the Kajdan Lustig basis would go to those IC sheaves, assuming that you've traveled along this correctly. But I don't know that for sure. I would need to check that.
Okay, thanks.
Okay, more questions? Okay, this does not seem to be the case. So yeah, let's thank Laura again.
Can I just say that it has been a really interesting semester of seminars, and we've had some from some pretty exotic locations. And so I think we should give Arik a big hand for setting this up this semester.
Yeah, thanks, Eric. I appreciate that as well.
You're welcome.